Hello, my name is Ju-Hong Min. I'll present our paper, Convolutional Hough Matching Networks, which is joint work with Min-Soo Cho. In this work, we introduce the Hough transform perspective on convolutional image matching and propose an effective neural matching module using a high-dimensional convolutional matching kernel. The proposed method can be used for various challenging matching problems, in particular with deformation and intra-class variations. Visual correspondence is a fundamental computer vision problem with numerous applications such as object recognition, visual tracking, and 3D reconstruction. In this work, we focus on semantic correspondence, which aims to establish correspondences between images depicting different instances of the same object category. The Hough matching algorithm is an effective matching method which exploits duality between parts and parameters of the objects. Basically performs voting in the dual parameter space of the target object called Hough space, where votes from the object parts are accumulated to form local maxima in the space. Despite its good empirical performance, the Hough matching method is limited in the sense that the Hough space is shared for all candidate matches, and this makes it less accurate and weak to background clutters. To address the issue, we create a local and individual voting space for each match. In other words, we convolutionalize the Hough matching algorithm. First, we introduce local windows around regions X and X prime. Since the local voting space is now dedicated to X and X prime, we can simply assign a match score V for a candidate match by taking the vote value at the bin with offset 0. Then, the equation can be generalized to a form of 6D convolution with an arbitrary kernel K. The convolutional correlation tensor is, in turn, the local Hough matching in high-dimensional space. Note that this convolutional extension of Hough matching has a generic form, as it reduces to a similar form of 4D convolutions, when the Hough space is restricted to the center translation. It can generalize to higher dimensions beyond 6D, when additional transformation dimension is introduced, such as rotation, shear, and others. We can think of many parameter sharing strategy in perspective Hough matching, and we propose position-sensitive isotropy kernel, where parameters are shared if their distance to the center and the offset length are the same. With the CHM as a learnable layer, we introduce convolutional Hough matching networks, which consists of three main parts. We first construct multi-scale features by applying 3x3 convolutions on resized image features, and build high-dimensional correlation tensor using cosine similarity. Next, a CHM layer with 60 position-sensitive isotropy kernel takes the correlation tensor to perform Hough voting in the space of translation and scaling. We then perform max pooling to select the most dominant vote among candidate match scores in the scale space, and proceed another 4-dimensional convolutional Hough matching. The output for the correlation tensor is transformed into a dense flow field by applying soft argmax. Then, our training objective minimizes the Euclidean distances between the predicted and the ground truth key points. We now demonstrate our experimental result. As shown in the table, the proposed method clearly sets a new state-of-the-art on all the three benchmarks of the semantic correspondence. We also plot precision recall curves of the recent methods and ours, and the result verifies that our model effectively discriminates between semantic parts and background clutters. Thanks to the small number of parameters in CHM, its another huge advantage is the interpretability. Here we visualize learned 6-dimensional kernels where the arrows show the spatial displacements, and their color intensity represent the weight magnitudes. Interestingly, the weight patterns of these two kernels are remarkably similar. The weights for matches with large offsets and closer distance are learned to be higher, while those with small offsets and far distance are learned to be lower. Moreover, learned weight patterns of the full kernels in circles are noticeably similar to each other, which reveals that our position-sensitive isotropy kernel clearly benefits from its reasonable parameter sharing strategy in terms of both efficiency and accuracy. We also train our model with different channel sizes. Increasing the channel size typically harms the quality of the predictions. The results imply that the high-dimensional convolution on the correlation tensor may play a different role from the 2D convolution on image features. The role of the convolutional matching is to learn a reliable voting strategy, rather than to capture diverse patterns in the correlation tensor. Thank you for watching. Please see the paper or visit our poster session for details.